the sign of the times? Sorry? Sign of the times.
Hello everyone. Welcome to ICM lecture room. It's my pleasure and my honor to introduce the speaker, Samit Dasgupta and Mahesh Kakde. Samit Dasgupta is a professor at Duke University. He has received many recognitions, including a Sloan Research Fellowship and a Career Award from the National Science Foundation. And he's a fellow of the American Math Society. Mahesh Kakde is a professor at Indian Institute of Science, Bangalore. And he obtained his PhD in Cambridge University under John Coates. After a few years in Princeton and University of College London, he moved to King's College London University College London. He moved to King's College London in 2011 until 2019, before moving to his current institution. Without further ado, so the title of their lecture today is on the BRUMER-STARK conjecture and refinements. Mahesh and Samit, please.
Okay, thank you. I hope you can hear me. So there.
Mahesh.
Okay. So for the online audience, there is a chat section, and David Loeffler is kindly monitoring this, so he'll relay any questions that you have. So thank you, Wei, for the very kind introduction, and I thank the organizers of IMU for inviting us here to speak. It's an honor, and I especially want to thank the local organizers for making this event happen at such a short notice. Okay, so the plan is I'll speak for the first half, and I'll talk about BRUMER-STARK conjecture, and then Samit will talk about explicit formulae for BRUMER-STARK units. Okay, and we want to acknowledge the kind support of all these foundations which made the in-person meeting here in Zurich possible. Okay, so here's the setup. Okay, so F is a totally real number field, and I denote the degree of F over Q by N. And we want to study CM extensions of F, which are abelian. So H is a CM extension of F. It's abelian, and I denote the Galois group by G. So we want to study ideal class group of H as a Galois module. Okay, but before doing that, let me recall the L functions. So chi is a Dirichlet character, and so okay, so a priori it's a character from Galois group to complex numbers. And using class field theory, you can think of it as a function on non-zero ideals of F, and that's why I have here this chi p. Yeah, that's why I can write here this chi p of chi of p. Okay, all right. So we have the convention that if p divides the conductor of chi, then chi p is just 0. Okay, all right. So oops, it's gone ahead. Yeah. Okay. So this is the usual. Sorry. Yeah, I'm not sure how to get rid of that. Perfect. Yes. Thank you. Okay. All right. So so the L function is defined by this Euler product as usual. And a priori, it makes sense for real part of S bigger than 1. And then, as we saw in Caligari's talk this morning, it has a meromorphic continuation to complex numbers. And it's usually entire if chi is not, I mean, it's if chi is not trivial, then it's an entire function. Okay. But for our particular setup, we need to modify it a little bit. Okay. And the way we modify it is we remove certain Euler factors and we multiply it by certain factors which we call T smoothing. So So S and T are finite set of places of F, and there are some mild assumptions on these. These are required for the integrality and the rationality statements that I'm going to talk about later. So S contains all Archimedean places of F, and S contains all places of F that ramify in H. And T is a non-empty set which is disjoint from S. It's also finite, and it's large enough in the sense that either it contains two primes of distinct residue characteristic, or it contains a prime whose residue characteristic is bigger than degree of, so this n plus 1, okay, degree of F over Q plus 1. Then we denote the L by L sub S T chi comma S, this modified function where we remove the Euler factors which are not in, which are in S, okay, and the infinite things were already not there by the previous page, and we modify it at T in this particular way, okay. So this is a factor which will make everything integral. All right, so moving on, that was one side of the story. The other side is we have this P unit group. So you take all the U's in OH 1 over P star, so P unit. So it's norm at places which are at primes which are not above P is already 1, but we also need it for Archimedean places. Okay, so all U such that the W-adic mod is 1. So in particular, if you take complex conjugation and make it act on U, you get U inverse. Okay, so these are what are called anti-units. Moreover, we need this U to be congruent to 1 mod all primes above primes in T in H. Okay, so this is 1 mod U is 1 mod Q for all Q in T. That will, with our condition on T that it's large enough, this will just make U T minus torsion free, but it's somewhat better than that, as we'll see in the results. It's implicit in that. Okay, so what's the conjecture of Stark in this particular setting? So you fix a prime capital P above small p in H. Okay, then Stark's conjecture tells you that there exists a P unit, an element in this UT minus, whose p-adic odd and p-adic odd of all its conjugates is related to this modified L value in this particular way. Okay, so if you take if you take this odd of U at all primes of H above R fixed prime P, then this L value is given by this particular formula. Okay, so summation chi sigma odd of sigma inverse PU. All right. So that's the conjecture. So somehow implicit in this statement is some algebraicity. There is a claim about these L values, but this was already known. Okay, so as I'll say on the next slide. All right, so so that's Stark's conjecture. So here is our result. Before I kind of discuss other things related to this. So this conjecture holds up to 2. Okay, so as long as you invert 2. So as long as you can take sort of powers of U, two powers of U, you can show this formula. Okay, so before that, let me maybe I should have remarked. All right, yes. So if you tensor UT minus with rational numbers, then Dirichlet's unit theorem gives you that UT minus tensored Q is isomorphic to minus part of QG, the group ring over G, and then this can. So this conjecture is kind of this claim is trivial in UT minus tensored with Q. Okay, so the real content of the conjecture is that there is an integral element, and so okay. All right, so so we prove it away from p equal to 2. So we cannot show that there is an element u in ut minus, but ut minus tensored z1 over 2. And later on, perhaps I'll remark about what goes wrong at 2, but it's not just a technical thing, okay? There's some conceptual thing that we need to understand at p equal to 2. And so the proof for p equal to 2 is requires new ideas, I think. All right, so so that's our theorem. Now there's a higher rank version of this, and what I mean by higher rank is if instead of fixing one prime Gothic p in F, which splits completely in H, I can take finite number of primes, let's say R. And then it would be a statement about an element in not just this, but somehow wedge power of this tensored with Q. Okay, so there's an element in that related to L values in a certain way, and the conjecture would say it has some sort of integrality property. Okay, it doesn't really lie in the wedge power of ut minus. But Rubin formulated a precise conjecture, and we can prove that conjecture also using our using the strong form of BRUMER-STARK that I'll state in a few moments. Okay, all right. So here's a precise form of this algebraicity statement that I was telling you about. So if you take this L sub S comma T chi inverse of 0, then these are a priori complex numbers. So there is a theta in CG, okay, with complex coefficient, which interpolates all this. So if you take any character of G, evaluate an element of CG, you get this complex number out of it. But it's a deep and beautiful result, firstly due to Ziegel and Shintani, that this element theta actually lives in QG. For that, you don't require this modification at T. But when you do this T smoothing, Delin and Ribet, they refined Ziegel's method, and Casaunogas refined Shintani's method to actually show that you get an integral element, okay, something in ZG. Okay, so this is the element that we are going to work in, and so we'll next look at a reformulation of this statement that Stark made, and this reformulation is due to Brumer. So that's the so we'll call it the Brumer-Stark conjecture eventually. Okay, so so we take this class group attached to H. So this is denoted CLTH, and this is the class group of conductor given by product of all primes of H, which are above T, primes in T. So very explicitly, this is just defined as taking all the non-zero ideals of H and modding it out by all principal ideals, which can be generated by U, which is congruent to 1 mod T. Okay, so this is slightly bigger than, possibly bigger than the class group of T, because you allow tame ramification at primes in T. It annihilates the class group. Okay, so that's the statement. It's enough to prove the statement prime by prime, and that's what we are going to do. We'll do it for all odd primes. Okay, so we can't do it p equal to 2. All right, so well, we actually don't prove that statement directly. We prove some strengthening, and I'll tell you why the strengthenings are essential. Before that, let me very briefly recall what a fitting ideal is. So for a finitely presented R module M, you take a presentation, and here I can assume that N is bigger than or equal to M. Then the 0th fitting ideal, or the initial fitting ideal of M, is the ideal generated by all M by M minors of F. So it's kind of a old result that this is independent of the this ideal is independent of the presentation you take, and it gives you something which is contained in the annihilator ideal. So this is a stronger invariant of the module. And just as a side note, we if you can take n to be m, then we say that m is quadratically presented, and in that case, the fitting ideal is principal. So you can imagine that this would be rare, that fitting ideal is principal. Okay, so here's the stronger version that we prove. This was So here the check here means you take Pontryagin dual, and the minus means that you take the part of the module on which complex conjugation, which is a well-defined element in G, acts as -1. Okay, and so here P is odd, so defining this minus part is not a problem. Okay, all right. So this was. Okay, two remarks. So in general, it is false that theta belongs to the fitting ideal of the class group without taking the Pontryagin dual. This was observed by Kurihara and I think in the function field case by Popescu. And so they made this conjecture, and the evidence for that was that follows from the equivariant Tamagawa number conjecture. Okay. All right, so you can ask what exactly is the fitting ideal of this Pontryagin dual. This was conjectured again by Kurihara, and this is we also proved that statement. So it has some precise description in terms of this ideal. Okay, and you can ask if there's an arithmetic object whose fitting ideal is given by your theta that you're interested in. So this is a more vague question, but fortunately this has a nice answer. And this was conjectured by BURNS, Kurihara, and Sano. Okay, so this nabla is some Ritter-Weiss module or Selmer module, and they give a precise construction of this Selmer module, and they conjectured that the fitting ideal is generated by this theta. So this nabla has quadratic presentation. Okay, so one thing that they prove. So the fitting ideal is principal, and it's generated by theta. All right, and what's the relationship between nabla and the class group? Well, there's a surjection from this nabla to the class group, which means that the fitting ideal of nabla is contained in the fitting ideal of the class group. Okay, Pontryagin dual of the class group. And so by this theorem, we get the theorem on the previous page, and hence we get the BRUMER-STARK conjecture. Okay. All right, so, okay. Okay, so maybe a few remarks before I say a word or two about the proof. So the BRUMER-STARK conjecture is strong enough to give you results on equivariant Tamagawa number conjecture. Okay, so equivariant Tamagawa number conjecture, it says something about kind of it is an integral statement which relates leading terms of L values to some arithmetic object in a very precise way. And the strong BRUMER-STARK conjecture, it implies equivariant Tamagawa number conjecture, at least away from p equal to 2. So this was recently deduced by Bullock, Burns, Dowd, and Seo in general, so away from p equal to 2, and also by Atsuta and Kataoka in some cases. So the two methods are sort of quite different. The first, Atsuta and Kataoka, they basically mimic our methods and prove ET&C in the cases that they can do. Whereas the Bullock, Burns, Dowd, and Seo, they just use some Euler system machinery to deduce ET&C from our result. Okay, and so this as a corollary, you get a higher rank integral Gross-Stark conjecture that Samit will speak more about. Okay, now let me say a word about the proof. So this diagram is due to Barry Mazur, his article on RIBETS work, in particular of constructing abelian extensions which are unramified. Okay, so you want to start with L functions and you want to go to class group. Now, the way to do this is you first go to Eisenstein series, and on the next couple of slides, I'll try to be a little more elaborate about this. From Eisenstein series, you go to CUSP form. The relationship between L functions and Eisenstein series is that Eisenstein series appear as constant terms of, L functions appear as constant terms of Eisenstein series. And modulo this L functions, your Eisenstein series looks cuspidal, okay? So you actually construct a CUSP form, which is congruent to your Eisenstein series modulo the L function you were looking at. And CUSP forms are related to Galois. CUSP form gives you Galois representation, as we saw today. From Galois representation, you come up with some Galois cohomology classes, and that gives you the class group. Okay, so just very briefly, some details. So if so there's a way to one Eisenstein series, at least if you're not working over Q, this is all literally true. At Q, you need to modify something which has the constant term theta as constant term as theta up to powers of 2 in any case, and it has a very explicit Q expansion. So modulo theta, this looks like a CUSP form, okay? And so we actually construct a CUSP form. So you start with such a linear combination, which has constant term 0 at infinity. And here V and H are some forms which are not really explicit, but we know something about their constant term, and we know something better about VK. So VK is just a lift of Hasse invariant, and HK has coefficient precisely to make things kind of cuspidal. So these are non-trivial things to show existence of. They come from algebraic geometry, and this is the precise thing that we need is in a paper of Jesse Silliman, which builds on work of Hida and Chai. Okay, so you get a CUSP form F, which looks Eisenstein. Okay, so you understand its action of Hecke operator on it, modulo theta, and so you take Galois representations attached to the eigenforms in the Hecke orbit of F. That gives you cohomology class, and you can get a cohomological description of your nabla and construct elements in this nabla. So this is, and since everything is happening mod theta, you kind of eventually show that you have constructed enough classes in nabla to give you that fitting ideal of nabla is contained in theta. Okay, so this is just an inequality, and it's in the opposite direction somehow than the one in BRUMER-STARK conjecture. But there's an analytic argument using class number formula which shows that this can be upgraded to an equality. So I'll end with a remark saying that it's really essential that the strengthening of BRUMER-STARK conjecture that we wanted was an equality to begin with, because RIBET'S method in general gives you an inequality in the reverse direction. Okay, yeah, so I'll stop here. I'll let Samit continue.
All right, so thank you very much. First want to begin by thanking the organizers, both the ICM committee for inviting us to speak and the local organizers for having this wonderful event here in Zurich. Very glad to be here. So now for my half of the talk, I want to speak about applications of our work to questions of explicit class field theory. So I want to start with the very classical theorem called the Kronecker-WEBER theorem, which tells you about the maximum abelian extension of Q. So before we've been dealing with a general totally real field F. So for this slide, F will be just Q. In class field theory, if we don't use the word explicit, class field theory tells you about the Galois group of the maximal abelian extension of Q over Q. And it tells you that it's isomorphic to the units in the ring Z hat, which is just isomorphic to a product of ZP star as P ranges over all the prime numbers. Now, when you throw in the word explicit, what you're asking is, what is the field itself? What is QAB? Not just what is its Galois group. And that is given by a theorem of Kronecker and Weber, which says that QAB is obtained by adjoining to Q all the roots of unity. So any finite extension of Q that is Galois with the abelian Galois group is contained in a cyclotomic field Q adjoin e to the 2 pi I over n for some n. Okay, so the question of explicit class field theory in general obtained more fame in the 1900 Congress when Hilbert stated his very famous 23 problems. Right in the middle of this list of 23 problems was his 12th. And I'm going to select some excerpts from Hilbert's article on the 12th problem. The theorem that every abelian number field arises from the realm of rational numbers by composition of fields of roots of unity is due to Kronecker. So this is just the Kronecker-Weber theorem that I explained on the previous slide. Since the realm of the imaginary quadratic number fields is the simplest after the realm of rational numbers, the problem arises to extend Kronecker's theorem to this case. So this is often known as Kronecker's Jugendtraum, his dream of youth, to try to establish the maximal abelian extension of a quadratic imaginary field in a way that's analogous to how Kronecker and Weber established the maximal abelian extension of Q. Then we continue. Finally, the extension of Kronecker's theorem to the case that in the place of the realm of rational numbers or of the imaginary quadratic field, any algebraic field, whatever is laid down as the realm of rationality, seems to me of the greatest importance. I regard this problem as one of the most profound and far-reaching in the theory of numbers and of functions. So already at this time in 1900, Hilbert realized that Kronecker's Jugendtraum was just the beginning of the story. Already at that time, through Kronecker's work and the work of others, they kind of knew what the answer to quadratic imaginary fields should basically look like, and they were very close to getting it. And then later in the 1900s, this was fully established. So, but for many, many years after that, it's been open to know how to generate the maximal abelian extension of arbitrary number fields. It's clearly a leap going from these fields, Q and quadratic imaginary fields, which have trivial unit group, as something that kind of unites them, or I should say finite unit group, versus general number fields. Okay, so now let me bring this back and make a connections with what Mahesh spoke about, the BRUMER-STARK and Gross-Stark conjectures. So now let's put ourselves in the setting of a totally real number field. So for example, you could take a real quadratic field, a Q adjoin the square root of a positive integer. And let's let H be a finite CM abelian extension of F. Then the BRUMER-STARK conjecture predicts the existence of certain elements in these extensions you're trying to construct. These finite extensions that are Galois with the abelian Galois group, those are exactly the extensions you're supposed to try to construct in explicit class field theory. And the BRUMER-STARK conjecture is sitting there predicting the existence of certain special elements in those fields. And it's telling you that there should be units that are related to L functions of F in a specific way. And this is nice because the L functions of F, even of this extension of F, those characters, you can compute them intrinsically to F. That is, by class field theory, you can view the character of a Galois extension of H as something, as a ray class character, as something sort of intrinsic to F. So only knowing F, you can compute the L functions. And so you could see that knowing stuff only about F, you know that there should be elements in these extensions that you care about that somehow are related to those L functions. So this is a glimpse that we might be able to construct the fields, or at least certain special elements in the fields, using L functions. Now, the Gross-Stark conjecture is a refinement of the BRUMER-STARK conjecture that predicts that, furthermore, those same elements that are predicted to exist by Brumer and Stark are related to p-adic L functions in a specific way, whereas the BRUMER-STARK conjecture had to do with p-adic valuations, or ORDs, as Mahesh wrote in his slide. The Gross-Stark conjecture relates those same units to the p-adic logarithms of those same units to the p-adic L functions rather than p-adic ORDs. Okay, now I refined Gross's conjecture, beginning with my PhD thesis and then developed in further works, many with collaborators, but to give an exact formula for the BRUMER-STARK unit. So not just the p-adic logarithm of its norm, but actually just given on the nose, what is the p-adic formula for this unit? And it'd be a little complicated to give the exact formula here, but I can try to give a sketch of what that formula looks like. So in the specific case, when your prime ideal is just generated by a rational prime p, then it has a particularly simple form. This conjecture says that the unit U, the BRUMER-STARK unit, is a specific power of P that's described by the BRUMER-STARK conjecture, which power goes there, times a multiplicative integral. So this is an integral over the units of the completion of the ring of integers of F at P, and of just the simple function X. And what's interesting here is not the function you're integrating, but the measure that you're using to perform the integration. So this funny integral with an X through this through the symbol, this is a notation I think is due to Darmon. This is a limit of Riemann products instead of limit of Riemann sums. So it's just a usual integral in a sense, except you take products instead of sums. And this interesting measure mu is defined using the Eisenstein cocycle. So the Eisenstein cocycle has a very rich history. You could give an entire talk just, or teach an entire course on just the Eisenstein cocycle. I should say it starts maybe with Siegel's work when he showed that integrating modular forms gives you a cocycle property, and he studied this for the Eisenstein series, which is why it's really called the Eisenstein cocycle. Later, completely different approach to the Eisenstein cocycle has been taken by others. So Glenn Stevens had work on the modular curve in the 80s, and then David Solomon noticed that Shintani's method of studying zeta functions had a sort of cocycle behavior, and he studied this in low degrees, degree 2, degree 3, and then his colleague in London, Richard Hill, then generalized this to arbitrary degree. There have been many other approaches taken. A recent work of Bergeron, Charleroi, and Garcia studying integration of more general Eisenstein series on certain locally symmetric spaces, generalizing Siegel's construction, and work of Balance and Kings and Levin using the topological polylogarithm. There's also a method, a completely different method due to Czech using convergence, certain interesting convergent sums. So there's lots and lots of different methods to construct this Eisenstein cocycle. Okay, but so what do you get out of this? You want to get an Eisenstein measure. So I'm going to try to describe this Eisenstein measure as this I won't describe the cocycle property, but just how do you get a measure? And I'm going to describe it using Shintani's method. Okay. So what one does is one considers the group of units. So if you think of a real quadratic field, the group of totally positive units congruent to 1 modulo some ideal n, this is just cyclic, generated by one element, which you might call epsilon. You look at a fundamental domain for the action of this element on the totally positive orthant. Okay, and so for a real quadratic field, this is just a positive quadrant, and you have one element acting, and so you just get a cone. And those are the kinds of cones that you get. In general, Shintani showed that you can take a union of cones like this, simplicial cones, to get a fundamental domain. And once you have such a domain, and you can be more general and talk about a signed fundamental domain, so you could talk about, one cone minus another cone instead of just taking disjoint unions of cones, then you can take what's called a Shintani zeta function, which is at the bottom of this slide. You could take the sum of 1 of normative alpha to the s, as S ranges over all elements of that cone that are in some fractional ideal of your number field. And you can add sort of a congruence condition. So you could take a compact open set U of OP and ask for only the elements that lie in that compact open set. So this compact open set might be the set of elements congruent to 5 modulo P to the 6th. And then that would be sort of a congruence condition. And then it's sort of clear that that these zeta functions satisfy a certain distribution property. That is, if I break up U into a disjoint union, then the corresponding zeta functions add up. Once you have that, it turns out, so Shintani proved this, that these functions have analytic continuation to the entire complex plane. And via Shintani's formulas, what we proved is that if you do a certain smoothing process, is very similar to the T smoothing that Mahesh introduced here. T contains just 1 prime, which is a Gothic L. And then this is what the T smoothing formula does. What we proved is that mu then becomes an integer, not just a rational number. So you sort of using Shintani's formulas, we could study their integrality properties and prove that you actually get an integer. So you get a Z valued measure on OP. Okay, and that's let me just go back. That's the measure that you use in this integral here. So that sort of complicated slide that I just finished tells you what the mu is. So you integrate with respect to that measure, just the function x, and then the conjecture is that gives you the BRUMER-STARK unit. Okay, and the thing is, you can actually do this on a computer. This is really computable, and I really mean in practice. So let me just give you an example here. If you take Q adjoins square root of 305, right, and you say, we want to construct the narrow Hilbert class field. Okay, class field theory tells you that that's a cyclic degree 4 extension. So I'm going to take the prime p equals 3 because that splits completely in that extension. And we're going to compute the BRUMER-STARK unit. So you compute these p-adic integrals using the p-adic integral formula I gave on the previous slide. And I have two students, Yijie Liu and Max Fleischer at undergrads at Duke University. I have them sort of code these formulas. And by the way, you have to do something more intelligent than just computing the Riemann products. You have to have a more efficient algorithm. So you can compute the moments of this measure and use that to compute the integral rather than the dictionary definition. Anyways, you compute these p-adic numbers, and you can compute them to 100 p-adic digits. And then you have not just the unit, but the conjecture gives you a formula for all the conjugates. So you can take the elementary symmetric polynomials of all those conjugates of the unit conjecturally at this point, and you can ask the computer, is this close to an actual integer? And the integer, the computer comes out, oh, it's close to 9. Right, you have these complicated p-adic numbers with 100 p-adic digits, and then everything cancels, and you just get like 9 or 345. Then you know that you've probably gotten something right. And sure enough, you ask the computer after the fact, I've written down this polynomial. What does the splitting field look like? And you can check, you can prove rigorously that this is an unramified abelian extension of F. So I just want to stress that you're never telling the computer the extension you're trying to construct in any way. You just tell it that you want to compute the Hilbert class field of this field, and you give it these integrals, and then it spits out this equation, which you can show generates the splitting field. This is the Hilbert class field, the narrow Hilbert class field of this F. Okay, so I'll just do a larger example just to show you numbers grow. I took Q adjoining root 473. So by the way, this slide and the previous slide, the D is just the number at the top. So the tier D is 473. Took P equals 5. And you can do all these integrals, and you get this degree 6 polynomial. And sure enough, at the end of the day, you can ask the computer to, hey, is this generate a Galois extension of F? And it does. And is the Galois group abelian? It is. Z mod 6Z. And then you can check the ramification. You can check the discriminant and check the ramification. It's an unramified extension. So this is, you are correctly generating the maximum, the narrow Hilbert class field of these fields. Okay, so now I'll say something theoretical now that I've done these computations, which is that Mahesh and I have essentially proven that this formula is correct. So conjecture that I first sort of stated in my PhD thesis. So theorems that assume P is odd and unramified in F, then the conjectural exact formula for BRUMER-STARK units that I stated holds up to a bounded root of unity. It's really just root of unity in the field that you're starting with. So if the first case I looked at, if P is an inert prime in a real quadratic field, then it's just a P squared minus first root of unity that you could have an error of. Mahesh's student, Matthew Honor, has recently removed the root of unity error, except for possibly a 2-power root of unity. 2 is always a troublesome prime. Okay. If you only care about generating the maximal abelian extension, of course, you don't mind roots of unity anyways, because those always generate abelian extensions. Okay, so now let me get back. I motivated this all by explicit class field theory and Hilbert's 12th problem to generate the maximal abelian extension. How far can we get? Well, we show is that we can actually generate essentially the maximal abelian extension of F. So if H is a cyclic CM extension in which P splits completely, then the BRUMER-STARK unit for that extension can be shown to generate the extension. So it follows that if you take all BRUMER-STARK units and you allow yourself to range over all primes, then you get basically all CM extensions, okay? Of course, any field is generated by its cyclic subfield. So you basically get all the abelian extensions, except that there's the CM condition. But to get rid of that, there's a simple matter of adjoining the right square roots to get all signs. You need to adjoin square roots of elements of all possible signs. Then those together with their BRUMER-STARK elements will generate the maximal abelian extension of F. So in some way, we've sort of solved a question at the heart of what Hilbert was interested in, which is generating the maximal abelian extension of these totally real fields. So of course, Hilbert had a very different answer in mind. There was more to his essay, which I didn't include in my slide, which included some specifics about wanting sort of complex analytic functions with certain transformation properties. And of course, we've taken a completely different approach than what Hilbert had envisioned. Okay, so let me just say, a few words. I won't get into any details of the proof about some things that go into our proof of this exact formula beyond what we saw in the proof of BRUMER-STARK. So Mahesh already mentioned there's this higher rank Gross-Stark conjecture, integral Gross-Stark conjecture, which of course begins with a very beautiful paper of Gross on behavior of Stark units and under the reciprocity map of a tower of fields. And a generalization of this conjecture due to Popescu and Rubin. And so we basically deduce that formula from our work on BRUMER-STARK. And we show that formula actually implies this p-adic integral formula. So that's kind of the key idea. And how do you do that? There's an important idea that was suggested to me by Richard Taylor, which comes out of course, his work with Taylor, with his work with Wiles, excuse me, on introducing auxiliary primes to a certain our set S that Mahesh had. You introduce auxiliary primes that are congruent to 1 modulo higher and higher powers of the prime P. This is often known as horizontal Iwasawa theory and was developed by Wiles in his early works in Iwasawa theory. So this is a really powerful method that we use in our formula. So if you'll indulge me for a second, I want to conclude first by thanking you, the audience, for your attention and your interest in our work. And also our families. So here we have pictured at the top. So Mahesh and I both want to thank our families for the love and support they've given us during this time. On the top, we have Mahesh's beautiful wife, Tipashri, and daughter, Nithyana. On the bottom, you have my younger daughter, Serena, my older daughter, Shayla, my new baby, Ishan, amazing wife, Smriti, my mother and mother-in-law, who have both helped so much with the kids during crazy pandemic time when we've been trying to do this work. So thank all of you and thanks to them. Thank you.
Thank you, Mahesh and Samit, for your beautiful lectures. So the questions for the audience worldwide are provided on Discord, right? So so the lecture for the live stream now is concluded by everyone.
So far, there don't seem to have been any questions asked on the Discord feed.
Okay, so that's good. Maybe more are coming on the way.
Meanwhile, I think we can have some questions from the live audience. If anybody wants to ask any questions here in Zurich?
Yes, please.
Anyone? Okay.
Oh.
What's the relationship between the different polynomials you get if you change the prime auxiliary prime L? Is there a relationship?
That's a very good question. So you're talking about these.
Yeah, exactly.
These polynomials. So you're talking about changing the prime L or changing the prime P?
L.
L. Interesting. Yeah. Those are related to one another. So basically, if I take the Stark unit for 1 prime L, say I have L1 and L2, maybe I can write actually. So I'm not sure if this is going to show up. So if I take is not, sorry, yeah, okay. UL1, if I take frob L2 minus 1, that's the same as UL2 frob L1 minus 1.
Right.
Okay. Frob L1, okay, applying a frob minus 1 means take, the Frobenius at L2 applied to UL divided by UL, that's what that means. But so that's the relationship for if you change the ULs.
Right.
If you change the P's, you're getting totally different elements. You're taking elements that generate different ideals. So there's basically no relationship between them, other than they somehow magically the valuation of one unit at the prime above P is equal to the valuation of the other unit at the prime above P prime, right? So changing P is two different units, but yeah, at Yale, it's kind of a mild change.
Right.
Well, maybe it's worth noting that it gives some kind of Euler system relations when you have UL1, L2, and so.